The AC equivalent circuit of this amplifier can be obtained by shorting the DC voltage source to ground and short circuiting the capacitors to form the AC equivalent of this form. To further simplify this circuit, we can see that RB1 and RB2 are coming in parallel. So they behave as a single resistance parallel to RB1 and RB2 like this. So RB is luckily the same equivalent resistance as found while themanizing the DC equivalent circuit of this amplifier. Now we can replace this transistor by its small signal model for further analysis, further analysis to find the AC parameters easily. Here, since the emitter is not directly grounded, so it would be better to use T model instead of pi model. Pi model can still be used, but it will actually not simple as compared to the T model. We will explain it later when providing the pi model of this circuit. But at the moment, let's have a T model which is more suitable for a transistor having emitter not directly grounded. So replacing this transistor by its hybrid T model, here we can see the base, collector and emitter, the current source, voltage controlled current source, and the early effect resistance between collector and emitter. Now we can connect the remaining circuit. Here at the emitter we have a resistance Re with respect connected to ground. At the collector we have Rc and RL parallel. At the collector we have Rc to ground, RL to ground. And at the base we have RB to ground and the practical signal source. RB to ground and practical signal source. And these are the parameters GM, RE and R0 newly introduced by the BJT T model. Without this, the AC equivalent model-based circuit is not completed. So these are the formulas. We already have derived these things. So by putting all these values for this amplifier under consideration, we got GM, RE and R0. And please remind that Re is also the resistance between base and emitter, but explicitly available at the emitter side. Whereas in pi model, we have R pi also in between base and emitter, but explicitly at the base side. And we already have seen that R pi and Re are equivalent. R pi is 1 plus beta time Re. Same is the relation between base and emitter currents. Now let's relate the other things. This is the stage of this amplifier. User has to plug in the DC voltage source, the signal to be amplified, and the load at which the amplified signal is to be loaded. And this stage is here for the AC equivalent circuit of this amplifier, right? So here we can see we need to find AV0 from input to the output of this stage, excluding the source and the load, right? AV is from the input of the stage to the load. GV node is from AC signal source to the output of the stage, excluding RL. And GV is the overall voltage gain, including the whole amplifier from the source to the load. So to find these parameters, we need to see what are the resistances and what are the voltages at the input and output of the stage. And this model based circuit give you an easy way to find the resistances at different points and the voltages instead of this circuit. For example, here we cannot see easily what is the input resistance facing by the signal source here. Whereas here we can see what are the input resistance feel by the signal coming out of this signal, the practical signal, right? And same will be the case for the R out and others. So let's find it with the model. So this would be the R in, this would be the R out of the stage, right? This will be the R input at the base. When we will see to the base, whatever the resistance feel by the current while entering the base will be the resistance at the base, right? So R in would be RB parallel to whatever is the resistance faced by the current entering into the base, right? What will be the output resistance of the stage? Here we can see RC would be occurring in parallel to what? A series combination of R0 and RE, or first the series combination of the parallel combination of these things and this. So it seems to be very difficult and it is out of your course. So I explicitly said that while writing a T model, you need to neglect the early effect, the R0. Okay, to find out the R out easily. And it is fair because R0 is usually very big, and whatever resistance comes in parallel, then that resistance leads, and the effect of this R0 becomes negligible. So let's take the model, still the T model, but without the early effect resistance, the R0. And now the output resistance of the stage will be nothing but only equals to RC, which is equal to 5 kilo ohm, right, for this amplifier. Now to find out R in, we need to find out R input at the base of this transistor, and to find out R input at the base of this transistor, what we need to do, we can see, and we already know that this RE is in pi model will be equal to R pi, and that R pi will be equal to 1 plus beta time of this RE. It means whatever resistance is at the base of T model is 1 plus beta time actually BC at the base, right? That's why R pi is equal to R 1 plus beta RE, right? So simple. You need to find out the total resistance at the emitter. So at the emitter we have this discrete RE connected as a circuit parameter, right, circuit component, and that resistance is coming in series with this RE. That's why T model is best for an emitter having resistance, right? So we can see this resistance is in series with this resistance at the emitter, internal resistance at the emitter, and the total resistance at the emitter will be the series combination of these two things. And when this resistance is to be seen from the base of this transistor, we already know that IB and IE have 1 plus beta relation, right? IE is 1 plus beta time greater than IE. It means whatever resistance is at the emitter is 1 plus beta time higher at the base. That's why base current is 1 plus beta times smaller than the current at the ammeter, right? So RE was 18, right? We found in the last slide. RE is 3 kilo ohm. So the total emitter resistance would be 3018.1 ohm, right? And when we multiply this with 1 plus beta 301, we get 908, almost 908.5 kilo ohm R input at the base. So it's much higher than this RB, which is 33.3k, right? So when we find the parallel combination of this resistance input at the base R small b and the discrete component based Theveninized resistance, the parallel resistance, got the same resistance here. Why? Because this resistance is very high. It means our input resistance is depending on this one, right? So this is actually reducing the overall input resistance. Otherwise, the input resistance is very high, right? So for these parameters, gain parameters, we need to find the output at the output of the stage, right? Output while including the load, like this one, right? So when we exclude RL, so what will be the voltage here? Excluding RL is the current in this output resistance multiplied by this resistance, right? So this resistance multiplied by the current. So this is the current, right? So product of these two will be the voltage here. But because this terminal is leaving the current leaving terminal, that's why we need to put negative sign. This is why we actually have an inverted signal at the output as compared to the input terminal, right? And the output voltage when we include RL not much different because R naught is now in parallel with RL. So you need to find the voltage here, right? And voltage here will be the current multiplied by the overall resistance, right? So current and multiplied by the overall resistance, right? Overall resistance, the current is going into this transistor, right? This will be the modeled current source. So this is your output when you include RL. This is your output when you exclude R, right? So now we can write the expressions for AB naught, AB, G naught,